Module 7. Implementing Sensor Fusion with AlgoBuilder. In this module, we will see an overview of ST's advanced motion libraries, which can be used to calibrate and combine sensor data for a variety of real-world use cases. Then we will see how we can use these libraries in AlgoBuilder and use MEMS Studio's evaluation features to examine the output of these libraries. As seen in this graphic, the X-Cube MEMS1 package comes with a variety of motion libraries, which when combined with ST's MEMS sensors, can enable scenarios including accelerometer, gyroscope, and magnetometer calibration, sensor fusion, activity detection, gesture recognition, tilt sensing, vibration monitoring, and many others. For more details on ST's advanced motion libraries, please see the X-Cube MEMS1 documentation. AlgoBuilder is capable of generating projects using many of these libraries, and so is an ideal tool for quick evaluation of these libraries with no coding needed. In this module, we'll use the Motion FX Sensor Fusion library to implement real-time 9-axis sensor fusion, which combines raw accelerometer, gyroscope, and magnetometer sensor data into an estimation of a platform's orientation in 3D space. It calculates quaternions, rotation vectors, gravity vector, and linear acceleration, and also performs gyroscope bias and magnetometer hard iron calibration. We will use the LSM6DSV16X accelerometer gyroscope combo sensor along with the LIS2 NDL magnetometer for this exercise. Let's get started. Return to MEMS Studio and click on the AlgoBuilder tab on the left side of your window. You may have your previous project from the last module already displayed here. If so, please first save any changes you've made to it by clicking the Save Design icon at the top of the window. Then to start a new project, click the New Design button at the top left. The New Design Firmware Settings window will appear. Click the Browse button to the right of the path box for the firmware location. Navigate to the root of your hard drive, then to MEMS Studio Workshop. Then open the Module 7 folder. Open the AlgoBuilder folder. Click the Select Folder button at the bottom. For the toolchain/IDE selection, be sure that STM32Cube IDE is selected. Then in the target list, select Nucleo F401RE plus X Nucleo IKS4A1 with the LSM6DSV16X. Then click OK. Now let's initialize the firmware directory for first use. Click the Initialize Project Directory icon at the top. A warning dialog appears to alert you that the directory will be overwritten. This is fine, so click Overwrite. After a few seconds, you'll see a message in the console window at the bottom indicating that the firmware directory has been initialized. Now let's save our design before going further. At the top of the screen, click the Save Design icon. You'll be prompted for where to save the project. Navigate to the root of your hard drive, then to MEMS Studio Workshop, Module 7, AlgoBuilder. In the file name box, enter Design and click Save. As we saw in the previous module, a new project starts out composed of a single functional block labeled Sensor Hub. This is the starting point for all projects and represents the main program loop, which is responsible for gathering sensor data from onboard sensors. Click on the Sensor Hub block. We can see on the right a description of the function block, and there is a control panel for setting the block's properties. In this case, the settable properties include the sensor sampling rate and full-scale measurement range. By default, these settings will configure the firmware to sample sensor data at 100 Hz, with the accelerometer full scale set to 4 Gs and the gyroscope to 500 degrees per second. These default settings are fine for this module. In the Library panel to the left of the main design pane, scroll down to find Motion FX9X. This represents the 9-axis Motion FX library. The 9 axes here refer to the data captured on each of the 3 axes, X, Y, and Z, on each of the 3 motion sensors, accelerometer, gyroscope, and magnetometer. Expand the Motion FX9X category. The available blocks represent the available outputs of the Motion FX library. The available calculations include gravity vector, heading, linear acceleration, quaternions, and more. For this module, we'll first use the rotation vector output of the Motion FX library. Click the rotation vector 9x block and drag it into your design. Drop it to the right of the sensor hub block. Now click this block to display its description. The description for the block indicates that its input node should be connected to the output of the sensor hub, and that the sensor hub should sample data at 100 Hz. As we have seen already, this is the default for the sensor hub, so we don't need to make any changes to it. The description of this block also defines the output data format being 3 floating point values representing the yaw, pitch, and roll of the platform. Connect the sensor hub to the rotation vector block by drawing a line from the sensor hub output node to the rotation vector block's input node. Let's use the value display block to print the rotation vector output. In the library pane, scroll up to the display category and expand it. Click on the value block and drag it to your design window. Drop it to the right of the rotation vector block. Draw a line from the output of the rotation vector block to the input of the value block to connect them. Click on the value block. In the Properties window, we see a set of pre-filled labels for the names of the block and values. Let's update these to match the input we've assigned. In the name box, change the text to rotation vector. In the Value 1 name box, enter yaw. In the Value 2 name box, enter pitch. Finally, in the Value 3 name box, enter roll. Now press Enter to save your changes. What we've done is enough to see these rotation vectors in MEMS Studio, but we can attach multiple functions of the Motion FX library to the sensor hub so that we can extract additional data in parallel. To demonstrate this, let's also use the Motion FX library to generate quaternions. This is another way to represent device orientation. In the library pane on the left, scroll back down to find the Motion FX9X module we used earlier. Under this, click on the Quaternions 9x block and drag it into your design workspace and drop it to the right of the sensor hub, below the rotation vector block. Click on the Quaternions block to bring up its description at the top right of the design window. We see a few important pieces of information. First, that the algorithm requires a minimum 100 Hz sampling rate of accelerometer, gyroscope, and magnetometer sensor data. Our sensor hub is configured for 100 Hz by default, so we do not need to make any changes. Secondly, the input needs to be taken from the output of the sensor hub. And third, the output of this block is 4 floating point values representing the calculated quaternion. Now draw a line from the sensor hub's output node to the input node of the quaternions block to connect them. Quaternions are often used to mathematically represent orientation in 3D space. They are used by many computing and visualization algorithms, but are not very meaningful for us to look at in their raw form. To help us with this, MEMS Studio has a built-in tool which will map a 3D model to these quaternions. In the library panel on the left, scroll up to the display category and find the fusion block. Click the fusion block and drag it to your main design and drop it to the right of your quaternions block. Then draw another line connecting the output of the quaternions block to the input of the fusion block. We are done and can now test our design. Click the build icon at the top of the window. This will generate the C code for the project and then build it. Once it is completed, you should see a message in the console pane indicating that the build process finished. Feel free to pause this video until your build completes. Before continuing, let's take a quick look at the generated source code. Click the Show C Code icon at the top of your window. This brings up the generated AlgoBuilder.c file, which contains the high-level program flow. At the top, we see the data variables used. We have the sensor hub output data, followed by a rotation vector array comprised of 3 floats and a quaternions data array comprised of 4 floats. This matches those blocks' descriptions we saw earlier. Below this are the outputs we have defined. We have the custom rotation vector output that we created to show the yaw, pitch, and roll. The sensor fusion display block is also defined here. Below this, there is the AB init function, which is called during firmware initialization. This initializes the sensor hub module, then initializes the Motion FX9X library. Finally, there is the AB handler function. This is executed at every sampling interval. This function initiates the process of gathering data, invokes the Motion FX algorithm with the new sensor data, and then serializes and transmits the results in the formats that we have described in our design. MEMS Studio reads this data stream when connected to the platform. This is only showing us the high-level flow, and there are many supporting functions. If you want to see more about how the firmware works at a deeper level, please feel free to open the project using STM32Cube IDE after you have completed this workshop. The project is located at the path given below. For now, close the AlgoBuilder.c file. Click the program target icon at the top of the window. If you receive a warning that the device is already connected, please click Yes to automatically disconnect. A new window will appear which shows the progress of the programming process. When completed, you should see a message indicating success at the bottom left of this window. You can then close this window. Go back to the Connect tab. Click the Connect button. If it is grayed out, try unplugging your board and plugging it back in. Once connected, MEMS Studio will detect the board's capabilities and automatically take you to the AlgoBuilder evaluation panel. Here you'll see all of the outputs that you configured in your design. In this case, we have the rotation vector and sensor fusion outputs. Click on the pink play icon in the top left corner of the window to start data capture. Click on the rotation vector option if it is not already selected. Here we see the calculated yaw, pitch, and roll of the platform. Move your board around and see how the numbers change. The yaw is rotation about the z-axis, and with the platform upright, is effectively the compass heading. Pitch and roll represent rotations about the y and x axes, respectively. Now click on the Sensor Fusion panel. This tool shows a 3D teapot model representing your board. As you move your board around in space, the teapot's relative position will also move corresponding to the board's motion. This is just one quick example of how you can use AlgoBuilder and the evaluation tools built into MEMS Studio to create a project that makes use of advanced motion algorithms without writing any code. There are many more functional blocks available in AlgoBuilder to experiment with, and we invite you to come back to this after the workshop. For more information on the motion libraries, please consult the documentation provided with the Xcube MEMS 1 function package at the URL given below. To prepare for the next module, please return to the Connect tab on the left side of the MEMS Studio window. Then click the Disconnect button. In this module, we saw an overview of ST's advanced motion libraries. Then we used these libraries in AlgoBuilder and used MEMS Studio's evaluation features to examine the output of these libraries. This concludes Module 7.